Okay, so in the last video we looked at the application of exponential growth to population growth models, and we used that differential equation that we introduced at the beginning of that section, or the beginning of this section, to sort of be our jumping off point. So we're going to continue working with that same differential equation but in different contexts now. And up next we're going to be talking about radioactive decay, something else you've probably looked at in a pre-calculus type of class. From observation, from experimental evidence, we know that the mass of radioactive substances tends to decay according to that natural law of decay that we introduced at the beginning of this section. So we're talking about the mass of a substance in particular, and if we let m of t represent the mass of a particular radioactive substance at time t, then what this is going to imply for us is that dm dt over m is constant. Remember, this is that relative, we called it growth rate in the past, or in the previous video, but it would be decay rate in this case. And it corresponds, I'm going to find the page where we talked about it before. It's coming from this right here, okay? So if I were to solve this for dp dt, I have this differential equation right here. But another way of saying that is that the relative decay rate in our case is constant. So this is that relative decay rate that I'm talking about. You notice I mentioned it right here, although not quite. There's a little alteration we're going to make to this. So if we're talking about radioactive decay, then dm dt would be a negative value. Remember, this represents the rate of change in the mass of our substance as time passes, and decay means that the mass is decreasing. So that decreasing trend means that we have a negative rate of change, but mass is always a positive quantity. So this is negative over positive, which is positive. If we want this to act like a real relative decay rate, a relative rate, we need it to represent a percent, and we want that percent to be positive. So what we do is we take the opposite of this. If this is negative, then putting a minus sign in front of it makes it positive. This is the quantity that we're going to call our relative decay rate. Okay? But going back to this little fact about radioactive decay implies this. If I solve for dm dt up here, setting this equal to k, I get this. And this is the same differential equation that we talked about at the beginning of the first video. In this case, I'm using an m instead of a y. That's the only difference. So with that said, we are also assuming that k is negative, because that's what would make this rate of change negative, as we just said is going to be the case in decay. If we let m naught represent the initial mass of the substance, then this would be the solution to this differential equation. M of t equals m naught, that initial mass, times e to the kt, where k is that relative decay rate right there, technically the opposite of that relative decay rate. So we're going to be working with functions of this type when we're looking at radioactive decay problems. Another important quantity that's associated with this concept is something called half-life. Half-life is a measure of time, specifically. It's the amount of time that it takes a substance to decay to half of its original mass. And this time is a constant. So if you have a radioactive substance, the amount of time it takes for 100 grams of that substance to decay to half of that amount, 50 grams, is going to be the same length of time as it would take for 2 grams to decay to half of that, 1 gram. So that amount of time is not dependent on how much you start with. And that's a consequence of the fact that we have a relative decay rate that is constant. So we're going to use these concepts in an example here. This says strontium-90 has a half-life of 28 days. And we have a couple of questions that we want to answer. First, if a sample contains an initial mass of 50 milligrams, we want to find a formula for that mass after t days. Now that formula is going to come from this. This is our formula, or our function for the mass of a radioactive substance. But in order to get a specific function for this case, I need two things. I need to know what the initial mass is, which we're actually given in this problem, and then I need to know that relative decay rate, K, or I need some other way of handling that. So let's start with what we do know. for part A, I'm going to have a function that looks like m of t equals m naught, which is 50, our starting amount, e to the k t. Now, we saw in the previous video, it actually was kind of helpful to rewrite this way. Okay? The problem doesn't ask me anywhere to find the relative decay rate. And you might assume that you have to do that anyways in the process of solving this problem, but if I can find what e to the k is equal to instead of just what k is equal to, I can make a substitution here. So now let's see what else we know. The half-life of this substance is 28 days. So what that means is if we start with 50 milligrams of this substance, then in 28 days, that's t, we should end up with half of that amount, 25 milligrams. So using this, that equates to 25 equals 50 e to the k to the power of t, okay? And if you don't like this method, you can work with this version of our formula, but I like this version better. So I'm going to do a couple of steps here. I'm going to divide both sides by 50 to get 25 over 50, which is 1/2. That equals e to the k to the power of t. Then if I raise both sides of this to the power of 1 over t, that'll cancel this t out, and I get this. 1/2 to the power of 1 over t equals e to the k. I'm not going to solve for k. Instead, what I'm going to do is use a substitution. Now, I actually just realized I forgot to do something because this is technically not correct, right? I have to plug something in for t to get 25, and we're told that that amount of time would be 28 days. So I should be putting 28 here. That was an oversight on my part. I'm going to try to be clever and turn all of my t's into 28s. It's not looking that great though. 28. Yeah. So really what we got here was e to the k equals 1/2 to the 1/28 power. So now what I can do is take this quantity and substitute it back here for e to the k. So now I have this, m of t equals 50 times e to the k, which I'm writing as 1/2 to the 1/28 power, to the power of t. But this is a power to a power, so I can simplify that. 50 times 1/2 to the t over 28, okay? Now, I chose not to do it in this section, but if you wanted to, we could generalize this really easily. Take a look at what shows up in this function right here. I have my initial mass, 50, and the half-life that I was given in the problem actually shows up in the formula, 28. In general, there was nothing special about the number 28 here. So if I'm doing any half-life problem, it turns out that similar steps will always get me a similar result. It's always going to look like the initial mass times 1/2 to the power of t over whatever your half-life is. That'll always work in any half-life problem. But you should know how to derive that. I prefer deriving it to just memorizing another formula. All right, so we have one part down, and now it says how long will it take the sample to decay to a mass of 2 milligrams? So 2 milligrams, that's a mass that goes here. 2 equals that guy. 50 times 1/2 to the t over 28 power. So to solve this, I can divide both sides by 50, which gets me 1/25, and that equals 1/2 to the t over 28 power. And then in order to solve for the t, I need to take a log with a base of 1/2 of both sides. So I'm going to have log base 1/2 of 1/25, but I'm actually going to choose to call it this. 25 to the -1 power. And I'm setting that equal to t over 28, okay? So this is where it's really helpful to have some logarithm properties under your belt. I can bring that -1 out, and I can also multiply both sides by 28 to isolate t. So that's going to give me a negative 28. Log base 1/2 of 25. But once again, I can't evaluate this in a calculator unless you have a nice, fancy calculator that you can input that base into. So I also need to use a change of base formula to evaluate this. I'll use the natural log. Log 25 over log 1/2. Plugging that into a calculator is going to get you a quantity of roughly, let's say approximately, 130.03. And remember, it said how long. This is a measure of time, and so far time has been measured in days. So that's 130.03 days. Okay? Cool. So that's another problem down, and that's the only radioactive decay problem that we'll do. For the sake of time, we'll go ahead and move on to our next application. Looks like I have some blank pages in here. All right. Our next application is going to concern something called Newton's law of cooling. And once again, if you have taken pre-calculus or college algebra or something like that, you have probably encountered this before. I just want to point out this light comes from my blinds, which are right there. So sorry if that's a little annoying. Hopefully everything is legible or readable. So Newton's law of cooling has to do with what happens when you take an object that's a certain temperature and you place it in an environment that has a different temperature. So we're going to do an example involving a cup of coffee in a minute. Let's suppose you take a hot cup of coffee and you set it on a table in just like your living room or something like that. The surrounding temperature is likely to be much cooler than the cup of coffee. So the cup of coffee is going to cool over time. It's not going to just keep cooling and cooling and cooling. It's going to approach room temperature. Because that's what the influence of the surrounding temperature is doing to it. Now, Newton's law of cooling describes how quickly that cup of coffee is going to cool towards that room temperature. It says that the rate at which the object is cooling is proportional to the difference between the temperature of that object at a given time and the surrounding temperature, the temperature of the environment that it's in. So for example, if your cup of coffee is 170 degrees and you place it in a room that's 70 degrees, that's a 100-degree difference between those two temperatures. We're going to call that a big difference. And so the cup of coffee is going to cool relatively quickly at first. But as it cools, its temperature is getting closer to the surrounding temperature. And so the difference between those is going to get smaller. Newton's law of cooling says that that's going to cause the rate of cooling to slow down as the coffee approaches that room temperature. Okay? This same concept applies to warming as well. If I take an ice cube, maybe an ice cube is not the best example, but something that's cold, something that's been in my freezer, and I stick it in the room. Now the room is warmer than the object, but the same concept will apply. The object will warm at a rate that's proportional to the difference between those temperatures. So we need some notation here. T of t, capital T of little t, is going to represent the temperature of our object, in my example, the cup of coffee, at time t. Where t equals 0 is going to represent, some initial time. The notation T with a subscript of S. So TS is going to represent the temperature of your surroundings. TS would represent the temperature of your living room, for example, in my example. So Newton's law of cooling, written in the form of a differential equation, says this: dt, so capital T and lowercase t. The rate at which the temperature of your object is changing is equal to a constant times the difference between the object's temperature and the temperature of your surroundings. Now this looks very, very similar to the differential equation that we introduced at the beginning of this section, but it's not exactly the same because the function here looks a tad more complicated. But with a variable substitution, we can actually see that it falls into the same category as that differential equation that we've used for population growth and for radioactive decay. To see that, let's set y equal to t minus ts. So dy dt, the derivative of y with respect to t, is the derivative of this. Remember, Ts is a constant. So when we take the derivative, that's going to go to 0. And the derivative of capital T with respect to t just looks like dt, like this. So we can make some substitutions. I can substitute a dy dt for the dt here, and I can substitute a y for the t minus ts here, giving me this. That's our original differential equation. So with a very straightforward substitution, we can see that this thing is technically that same differential equation, just in disguise. Let's try an example where we're using Newton's law of cooling. It says we have a cup of coffee with a temperature of 95 degrees Celsius, and it's in a 20 degrees Celsius room. When the temperature reaches 70 degrees Celsius, it's cooling at a rate of 1 degree Celsius per minute. When does this occur? When? That indicates that we're looking for a time. Okay. For this one, we're actually going to use the differential equation itself, not just the solution to that dE. We'll use that as well, but we're going to start here because the given in this problem, it tells us something about the rate of change in the temperature of our object. It tells us something about dt. It says that when the temperature reaches 70 degrees Celsius, it's cooling at a rate of 1 degree Celsius per minute. So using that up here in this differential equation, that's telling me that dt, which is equal to -1, it's negative because the temperature is decreasing. That's what cooling means, not increasing. That's equal to K times the temperature of the object, which at that moment in time is 70 degrees, minus the temperature of my surroundings. It says the room is 20 degrees Celsius. So that would be 20. This, of course, is equal to 50, which I have to divide both sides by that, and that gives me K equals -1/50, like that. Okay? So, now that we've established that, my next goal is going to be to find a solution to this differential equation. Now, we know that the solution to this differential equation is equal to this. Y equals y naught e to the kt. But for our purposes, what is y naught? Well, y naught represents the initial temperature of the room, right? Not of the room, I'm sorry, of the object. And we're told that here. It's equal to 95 degrees Celsius. So that means that I have y. Well, actually, hold on. Let's change things back in terms of t for a moment. No, I'm sorry. I don't want to get too far ahead of myself. What is y naught based on how we defined y up here? Y naught is equal to T of 0 minus my surrounding temperature. My surrounding temperature is 20 degrees. Okay? T of 0, the temperature of the object at time 0, is the temperature of the cup of coffee when I first introduce it to these surroundings. So that's 95. So y of 0 is equal to 95 minus 20, which equals 75. Okay? So that would be like what I'm putting right here. K, the K that's appearing here is what we solved for here. So that means y, which is actually equal to T minus my surrounding temperature, 20, is equal to y of 0, which was 75, e to the kt. So that's negative 1/50th times t, or negative t over 50. Alternatively, I could write that this way. T of t is equal to 75 e to the negative t over 50 plus 20. Okay, so this is the function that represents the temperature of my cup of coffee at a given time. Now it says, once again, when the temperature reaches 70 degrees Celsius, it tells us the rate at which it's cooling. When does this occur? So now really all we need to do is figure out at what time is the temperature going to drop to this exact level, 70 degrees. So to do that, I would plug 70 in for capital T. 70 is equal to 75 e to the negative t over 50 plus 20. If I subtract 20 from both sides, I'll get 50 here. And then if I divide both sides by 75, I get 50 over 75, which is the same thing as 2/3. 2/3 equals e to the negative t over 50. Now I would need to take a natural log of both sides, and I get natural log of 2/3 equals negative t over 50. Finally, multiply both sides by negative 50, and I get t equals negative 50 times the natural log of 2/3. Okay, so that's my actual time, but if I want to plug that into a calculator, which I just realized I didn't do that part ahead of time. I should have done that ahead of time. Let me compute that really quickly. That's going to come out to, what did we say? Negative 50 times natural log of 2/3. That comes out to approximately 20.27. And the timing that we've been using here has been minutes, or the units of time. So that would be roughly 20 minutes, 20.27 minutes. Okay? That seems pretty reasonable. A 20 degrees Celsius or 25 degrees Celsius drop in temperature in a room that's significantly cooler than that cup of coffee. From experience, 20 minutes seems like a reasonable amount of time for that to occur in. All right, let's see. Do we have enough time in this video for our last application? I think we do. I'm getting these blank pages out of my printer. There we go. Okay. One last application. This is something you definitely should have seen before in intermediate algebra and also in pre-calculus, I imagine. It has to do with compound interest. So in finance and banking and whatnot, when you make an investment in some kind of account that accumulates interest, there's generally two different types of interest that we could talk about. There's what's called simple interest, and then there's what's called compound interest. Compound interest is when you earn interest in an account, and that interest is always calculated against the current account balance, as opposed to the original investment amount. So when interest is first compounded, your account balance will grow by a little bit, and then the next time interest is computed, it's computed against the total amount that's now in the account, as opposed to what it originally started with. In addition to that, the way interest is compounded is we have a rate, an interest rate, which is given as a decimal, but you tend to think of it as a percent. And that there is a frequency with which interest is compounded over the course of a year. So that interest rate is an annual interest rate. If I say, for example, we're going to do one down here, that I have an account that accumulates interest at a rate of 2%. That's 2% per year. Compound interest, if you compound your interest at a rate of more than one time per year, divides this percent up by however many times you're compounding it. So for example, if you see something that says interest is compounded quarterly, that means 4 times per year. So we don't do 2% for each of those 4 times. That would cause you to accumulate money very, very quickly. Instead, what we do is we divide 2% by 4, which is 0.5%, and apply a 0.5% interest every 3 months. So that way you would get 4 in a year. You use that concept to derive this formula in an algebra class. A equals A naught times 1 plus r over n to the power of nt, where A by itself represents the account balance, how much money is in that account at some time. A naught is the initial investment, which we call principal. R is the interest rate, but as a decimal. So if it's 2%, I would write 0.02 for R. N, which occurs in 2 places, is the number of times it's compounded per year. Notice we're dividing the interest rate by that amount. So if it's quarterly, for example, N would be 4. T is the number of years that we're leaving this money in this account to accumulate interest. So this example I copied and pasted from your book just so you can kind of see how this works. If you have a $5,000 invested in an account that has a 2% interest rate and you let it sit there for 3 years, the amount that you'll end up with in your account varies depending on how frequently that interest is compounded. Annual compounding means you accumulate all of that interest at the end of the year. So you're dividing by 1. 1 plus 0.02 is 1.02. N times 3, N is equal to 1 again, so 1 times 3 gives me 3, and I get this amount, $5,306.04. If instead you compound semi-annually, that's twice a year, notice the interest rate has been divided in half. So the base of this exponential factor right here is smaller, but the exponent is also larger. So there's a trade-off that's sort of occurring here because I'm compounding more times per year. And you notice this trend kind of keeps happening. So we look at annual, semi-annual, quarterly, monthly, and daily compounding. Daily would be 365 times a year on a non-leap year. So as you can see, even though as we move down this list, we're compounding more and more and more times each year, the fact that there's this balancing act occurring between the decreasing base of this exponential and the increasing exponent means that this amount's not just going to skyrocket off to infinity as we increase the frequency over compounding. It will increase, but to a limit, right? You can see the difference between annual compounding and daily compounding is only about $3.13. It's not a huge difference. So what we want to do is consider what would happen if we let n go to infinity in this formula. Because we can break this down even further. What if you compound interest every hour, or every minute, or every second, or every millisecond, or every microsecond? What happens in the most extreme possible case? Well, if we think of compounding interest every instant in time, then we can kind of think of that in terms of what we would call continuously compounded interest. It's just continuously compounding. So we want to take our formula for compound interest and apply a limit to it as n goes to infinity. Now, in order to work this out, to see what this formula turns into, we have to manipulate it a little bit. So this is also copied right out of your book, but notice what we're doing. We're taking this exponent and we're splitting it apart. So from here to here, the exponent has changed from nt to n over r to the power of RT out here. Notice these powers would be multiplied and the R's would cancel out, taking me back to this step. Okay, now as we go from here to here, I'm bringing the limit into the square brackets. Since this is just a constant multiple and this is an exponent, we have limit laws that allow us to do that. Okay, the limit is now inside the square brackets. Finally, we're going to make a variable substitution. If we set m equal to n over r, then this exponent becomes m, and r over n is the reciprocal of that, so it would be 1 over m. And not only that, if n is being allowed to go to infinity, remember r is fixed, r is a constant, so this numerator is shooting off to infinity, which means the whole thing is also going to infinity. My limit still has the variable m this time going to infinity. Now the quantity that's on the inside here, we have seen this. This is the definition of the number e. So the entire thing in the square brackets here turns into e, meaning my function simplifies down to a of t equals a naught e to the rt. If you learned this in pre-calculus or algebra, you probably were calling a naught p for principal, and you may have learned this as the PERT equation, p e to the rt. We're just using different notation for principal here, but it's the same concept. Okay? Now, not only that, notice that if I were to differentiate this thing with respect to t, this is just a constant times an exponential function, and using my chain rule to differentiate, dA dt would just be equal to r, that's a constant, a naught e to the rt. Of course, a naught e to the rt is my function that we started with, a of t. So dA dt is equal to a constant times a of t. This is actually the same differential equation that we started this section with. We're just using an a instead of a y. That's the only difference. So what this means is that the rate of increase in the account balance, which is this, is proportional to the current balance at any point in time. Let's go ahead and do one final problem to wrap this section up using compound interest. So it says, how long will it take an investment to double in value if the interest rate is 3% compounded continuously? Okay, so remember, our function looks like this. A of t equals a naught e to the rt, but this time r is given to us, 0.03 t. Okay? Now we're not told what the initial investment is, but we are told what we want it to get to, double that amount. So I can write 2 a naught for what I want my account balance to be. Dividing both sides by a naught gives me 2 equals e to the 0.03 t. Take a natural log of both sides. Natural log of 2 equals 0.03 t. Solve for t. T is equal to natural log of 2 over 0.03, and that's where you want to use your calculator. This is approximately 23.1, and it's a unit of time, a measure of time, which in this case is going to be measured in years. So it takes about 23 years at a 3% interest rate compounded continuously to double your investment. Okay, that's going to wrap up section 3.8.